This is a brief tutorial on the fine-tuning of nature's fundamental constants. This is a quote from Stephen Hawking. The laws of science contain many fundamental numbers, such as the size of charge of the electron and the ratio of the masses of the proton and the electron. The remarkable fact is the values of these numbers seem to have been very finely adjusted to make possible the development of life. Stephen Hawking made reference to the fundamental numbers, or constants of science. This discussion will take a deeper look at these constants. What is a constant of science? What does it mean to fine-tune a constant? Why should we care? At the conclusion, a discussion on the universe fine-tuning machine and how it can be used to simulate the fine-tuning of 6 constants. To get started, let's look at 6 areas of science essential for understanding the world around us, its matter, its galaxies, stars, and life. The laws of science, as Stephen Hawking observes, requires the fine adjustment, or tuning, of the fundamental numbers of nature. This is illustrated by the following high-level coverage. Of course, many details are left out for simplicity. Let's start with mass. The mass values of about 15 subatomic particles are vital for our existence, such as the proton, found inside the atom. These 15 particles are essential to the standard model of physics. Some are very light particles, some are very heavy in a relative sense. Some particles have charge, but not all. Most of us know that electrons and protons have the same amount, but opposite charge. Of the many basic particles, 10 possess some amount of charge, not just electrons and protons. The amount of charge on a particle and its polarity are crucial elements to the makeup of our universe. All elementary particles have other defining characteristics besides mass and charge. But the other aspects aren't discussed here. Next are the 4 forces, gravity being the most commonly known. Isaac Newton described its effects in 1685. Gravity is crucial for how planets, stars, and galaxies form. The other 3 of the 4 are essential for the structure of atoms. Let's take a short detour and look deeper into the 4 forces. Electromagnetism, the weak and strong forces, govern the structure and dynamics of the atom. Gravity is largely responsible for the structure of the universe. Now, electromagnetism is well known by most people. Think magnets, radio waves. It also holds the electrons in a cloudy orbit around the nucleus. The weak force is responsible for radioactivity. It makes the sun shine. The strong force is indeed beautiful. It's double acting. First, it's responsible for holding the nucleus together. It binds protons and neutrons together. It turns out that these particles are themselves made of even smaller particles called quarks. So secondly, the strong force binds the quarks together to create stable protons and neutrons. But note the differences in the strengths of the 4 forces, indicated by these numbers here. The force of gravity is about 1,000 trillion times weaker than the strong force, normalized to 1 here. Electromagnetism is much stronger compared to gravity also. The individual strengths of the 4 forces are extremely fine-tuned. The values of the 4 forces are fundamental to our universe and life. The forces are part of the standard model of physics. These force values must have precise values, else no galaxies or life. Let's return now to the overview of the 6 areas of science that help form our understanding of the universe. Leaving the 4 forces, the next topic is cosmology, the science of the origin and development of the universe. It includes many facets such as Big Bang origins, galaxy and black hole formation, and mysterious dark energy. Dark energy permeates our universe and is about 70% of all of its energy. Now, scientists don't really know what it is, but they do know that its density value is crucial for our existence. The speed of light is one of nature's biggest mysteries. Why is it a rock-solid constant? Why is its speed in a vacuum 186,220 miles per second? Einstein developed his special theory of relativity on the relationship between space and time. But key to his theory is the speed of light being a constant. Finally, quantum physics. It's a somewhat weird branch of physics that describes nature at the smallest scales of energy, of atoms and subatomic particles. Classical physics deals with mass, charge, and spin, the four forces, and describes nature at ordinary, macroscopic scale. Quantum describes what classical cannot, reality at its core, ethereal and statistical in nature. Associated with each of the 6 scientific themes on this page are about 30 fundamental constants. These include the masses, the charges, the force values, cosmological constants such as dark energy, and quantum numbers such as Planck's constant. The precise values of each constant is vitally important to the makeup and structure of our universe. Notably, all the constants must be measured. None can be calculated based on principles. Let's look at one constant in more detail, the gravitational constant. What if it had a different value, say twice as big, or half its size? Would it make a difference to us? Next, let's look into this. Here is a logarithmic scale. It's not linear. The major ticks on the right side of 1 over here increase by a factor of 100 for each tick, up to a huge 10 to the power of 30. On the left side of 1, in here, the major ticks get smaller in a similar manner, down to 10 to the power minus 30. So 60 zeros of range across this scale. This is huge. If the gravitational constant g was larger by a factor of 2, we could break our bathroom scale by weighing twice as much. In theory, g could be more than a billion times larger, placing it, say, here. But it's not. Its actual value is here. Or it could be many magnitudes smaller, say, here. But it's not. It belongs here. It's a number with 11 zeros of smallness. According to physicists, if it was just a tiny bit weaker or slightly stronger, this arrow wouldn't even move on this scale, stars would not form or burn as they do, and life would not be possible. The same reasoning applies to all 30 of the important constants. This is a remarkable quote from Professor Michael Turner. The precision of the constants is as if one could throw a dart across the entire universe and hit a bullseye 1 millimeter in diameter on the other side. He's talking about fine-tuning and how amazing it is that our fundamental constants have the values that they do. An interactive web-based machine was created for exploring the miracle of fine-tuning. It enables users to simulate the tuning in of 6 fundamental parameters. You'll learn about each one, their allowed variations, and importance to our universe. This is the landing page of the machine website. It's a tease with no interactivity. On the left is a moving scroll with 10 essential constants in rotation. 3 are shown here. Mass of the neutron and its value are shown here. 10 dials here represent each constant respectively. When a constant moves into the center window, its corresponding dial will rotate to the correct value for that parameter. For example, mass of the neutron here is associated with Mn, this dial. This dial will then rotate to reflect this value. After all 10 are fine-tuned, the process repeats. Press Start to continue into the website. This is the main tuning page. On the left are 6 parameters that can be tuned. Here is the force of gravity, and at the bottom, mass of the neutron. A red LED indicates a parameter is untuned. A green indicates it is tuned. Choose any parameter to start tuning. The center dial is the current value of the selected parameter, pointed to here. Now, tuning occurs in 2 steps, coarse, then fine. When coarse tuning, you will hear a sparkle sound when close to the fine-tuned point. Next, move this switch from coarse to fine and continue tuning until you get a fireworks display, indicating tuning is complete for this parameter. The center display contains the parameter's title and 4 other elements related to the dial. The tuner is dual purpose. It's also a radio station tuner with many channel varieties. The bottom entry here shows the current channel information, the genre, and what's playing. The first time you tune in a parameter, keep the radio off. Here's the radio switch. Why a radio? For amusement, another form of tuning. Experiment with it. Use the Hints button to uncover the fine-tuned value and associated channel number. This makes locating the fine-tune point a snap. The goal is to turn all 6 LEDs to solid green and become a fine-tuning master. If you link to this tutorial from the UFT Machine website, return and select either the Learn More or Fine Tuner buttons to continue. If you link to this tutorial from another source, say within YouTube, please visit uftmachine.com to experiment with fine-tuning. For the best experience, use the Chrome or Safari browsers. No tablets or smartphones are supported.